Hello and welcome to our second lecture. Today I want to focus more on analysis and result. I will also talk a little bit about couplers. So here I have a very simple model which I made based on the last model I did in our last lecture. I have two arms and I fixed the first arm by using a fixed joint, which later I will turn into a revolute joint, and a revolute joint between the two arms. So as you can see, I don't have any pins. I removed all the pin geometries to keep the simulation simple and fast. But the pin is actually represented by this revolute joint. So if you here go to the friction tab, you see that you have a friction that is coming from a pin with radius of 15, which fits here, and the width of 20 and two washer caps of 18 millimeters. So basically the friction forces that you may have by having the pin here is actually here and included into the simulation. The only thing that is missing is, of course, the weight of the pin. But if the pin in your simulation is small, you can always follow this technique and make everything more simple and easy to solve. Now let's move on to result. As you know already, you can extract results by using this XY result view. Basically, by clicking on every item, you can go to the XY result view and review the parameters that can be extracted from that item, whether it is a motion body or a joint. So here let's move to pin 2 and take a look on some of the results. If now I click on the displacement, we already know that the displacement of this joint is 0 because it's not moving anywhere. You can double click on any item and it gives you two options. One is overlay and one is create new window. By clicking on new window, it will open a new graph window, and then if I click on overlay and click on the window that I want, this could be the main window or the graph window. It will overlay the new graph. I can do the same thing for the XYZ rotations. We'll open them in a new window. So displacements are all constant as we expect, so we can close. And now as you see on the absolute, here if you click on a motion body, you see that you only have the absolute, but for a revolute joint like this, you have absolute and relative because there is a base and action involved. You have two objects involved, so that's why you have absolute and relative. Note that basically there is no absolute in the simulation. Absolute here means that it is relative to the main coordinate system or the world coordinate system. And you can always find that by moving to the master part here. If I right click and click on open master part, I will go back to the modeling app where I can see my main coordinate system is located here. So this is called the world coordinate system. And of course you can change it inside the modeling app on your assembly. So this is the difference between absolute and relative. The relative will return the relative motions and forces between the base and action. Now on any graph, let's focus on this graph. On any graph, you can open the toolbar. If you overlay a couple of graphs, you can switch between them by using these two arrows. First, let's take a look on the x-axis, or the rotation along x-axis. Let me play again. So as you can see, we don't have any kind of rotation along this axis perpendicular to the screen. But and we expect a flat line, but you see a kind of a step or jumping value. The problem here is that for Rx, because it's absolute value, it is comparing the coordinate system of this rotating arm or rotating revolute joint with the board coordinate system, which is not moving. The rotation around x-axis is not changing, but it is changing direction. At this situation, the axis or the rotation around axis is clockwise, but as it moves to the other side here, now the rotation is counterclockwise because now the axis has flipped compared to the last position. And on every quarter, this is happening once. At the beginning of the simulation, if I start from beginning, the arm is crossing 3 quarters. That's why it is jumping up and down 3 times. But at the end, it just jumps up and down twice because it's only crossing between 2 quarters. And on every jump, it is switching 180 degrees. So that's the main problem with using absolute values of rotation. Let's move on to the rotation around z-axis, which is exactly as we expect. It starts around 180 and goes to 0 eventually. Now if we go back here, we have 3 other angles. These are called Euler angles or pitch, yaw, and roll. Now let's take a look on each one of them. This first one is the roll angle, which is exactly like the rotation as we expect. And then let me overlay the other Euler angles. And then the other two, which are now 0, constant. Because the Euler angle is the angle or the angular change compared to the coordinate system of the object itself. So it's kind of relative. But there is another problem with Euler angle as well. Let me go to the pin and flip the direction of the pin and then solve it again. Let's now take a look on the roll angle, which is the rotation, Euler rotation along the z-axis. Now we have a different plot. The problem with Euler angle is that it is using a wrap-up function. A wrap-up function is a function that basically wraps your values inside a range. The range here is plus minus pi or plus minus 180 degrees. It is trying to fit this angle. Let me open RZ. To this angle, which is between 0 and 250, tries to map that into plus minus 180. That's why after some values, it jumps up and down. Let me take a screenshot and take it to Paint. Here I can show what's happening on the figure. So as you can see, this part actually belongs here. And similarly, this part belongs to this point, and so on. So here we can see that after some angles, NX is cutting off after it reaches 180 or negative 180 and sends it to the other side. It seems like the rotation is flipped after hitting 180 or negative 180. Now the problem is that if you're using these values like Euler angles for calculating forces or doing some kind of control, you're going to have problem because it's constantly jumping between values. And this is the main problem with rotation actually. It depends on the application you have. you need to decide what happens after 360. Do you have 361, or you just consider it as one round or 1 degree? So you need to make a decision based on application you have. But there is a more straightforward approach here. Another option is to use markers. Markers are basically points that can represent objects. For example, I can put a marker anywhere on this object, which is the first arm. So I put a marker in the center of the arm 1 with this coordinate system, and I call it marker 1. I want to put the second marker here on the second arm, but I want to change the orientation system that aligns with the orientation of the arm. So I pick some point like that point. The x-axis I want to be in this direction, and the y-axis I want it to be perpendicular. Now you see I have a kind of, if I flip the x and y, so now you see that the coordinate system matches the other coordinate system that I want, and also it is oriented along the orientation of the second arm. Now if I click OK, call it marker 2, and now I have 2 markers, as you can see. Now I can click on markers, and then I get the same stuff that I could get by clicking on other items, like clicking on the joint. But here you can use a sensor to read the difference between the markers. For example, here I want to check the relative displacement, rotational displacement around z-axis between marker 1 and marker 2. And my sensor is called sensor 1. So if I now click on the sensor 1, and the XY result, I have this RZ value. But before we look into that, we need to solve the problem again. So the result reflects under the sensor. Now if I click on the sensor and take a look on displacement, now I see the displacement that starts around 45 degrees, around 50 degrees, because there is 50 degrees difference between these two, and then it changes based on the difference of angle between these two. There is also another option which is called a smart point. A smart point is exactly like a marker, but unlike a marker, you can't put it anywhere. It doesn't need to be on an object necessarily. So you can place it anywhere in the space, and then you can use it to compare anything to that point. So now let's take a look again on the sensor and see what we can do here. So on the toolbar, you have 2 arrows that you can switch between the overlays. Then you have some evaluate functions that basically do some calculation on your data. For example, you can use the RMS value, and this will give you a kind of average of this figure. If you right click outside of the plot, you will have very useful tools. The most useful ones that I'm usually using are the peak probe and fine tracking. The peak probing mode is actually a probing mode that is jumping between the extremums. So it's very useful to find the maximum and minimums. You can also click on the plot and right click and click on show min max marker. It will automatically show you the maximum and minimums of that figure for you. Another useful one is this fine tracking. So you don't need to play animation to find a specific result. You can move this bar around or go step by step. At any point, you can click on the create marker and it will create a marker at that place for you. To manipulate your result, you can move to the result tab and use this curve operation. Here you can see the graphs that are already open. Let me close this XY result view. Here you can manipulate this data by doing some math or other functions on it. For example, here I can see the absolute value of this by adding an absolute value and going back. I need to add the y-axis here. So by just double clicking on the curve, I can get the curve number and y function. And on the x, I can again double click to get the x function. I check the syntax and then it will give me two options of overlay and plot, like the ones that I already had. I'm going to overlay it on this, and now you can see it in blue. The absolute value of the plot is now overlay and shown in blue. So here you can see curve operation result, which is the absolute value, and you can see anything under 0 is now flipped up. So I could get the absolute value. Or let's say you want to calculate the frequency of this vibration. Let's say you have a component that works within a frequency range and you want to check if the frequency is okay for your component. Here you can click on the FFT. There are different methods that is a little bit advanced to talk about these methods of windowing, but I go with none to take all the function, and it will automatically generate this function for you, which you can plot. I'm going to plot it in a new window, and here we can see a couple of jumps in the frequency. Basically, the jumps show the fundamental frequency of that vibration. And if I now go with peak probing, I see three main vibration frequencies around 0.85 and 1. These are two main vibration frequencies. So this is how you can manipulate the data and do some math function on it in real time as you are solving the simulation. Now let's see how you can visualize data on the animation. If you open the result view of some objects that have associated data, for example, these data are actually associated with something inside the animation view, which here is the revolute joint. So if I on the revolute joint, right click on RZ, I can create a graph object. The graph object goes under the result under XY graphing. Now I have a new graph object here, which is the Z displacement. Now if I right click on this Z displacement, I can display it in animation. And if I go into the animation tab, along two arms, I also have the RZ displacement. And now if I play the animation, now I see another line representing this rotation. Now let's move to the other options that you can use under the Analysis tab. Let's start with the model check. Here, if you click on the model check, it will give you some basic report on what is wrong with the model. This is very helpful, especially if you get errors or you want to check if the results are valid or not. For example, I have a warning here that says M1 the marker that we made, the motion body thesis is not associated with geometry. A lot of things that you make here in NX motion should be associated with a geometry. For example, if we go and check this M1, you see here that the thesis is selected as dynamic. So it's just placed somewhere near the body or on the motion body, but it's not really associated to this body. And if it moves, it probably can't follow that movement. So you probably need to associate it to the body by selecting some geometries on the body that aligns with the coordinate that you want. Next, let's take a look at the interference. Interference, I don't have any interference in this model, so I can't actually try it. But basically, both interference and animation measure, they can trigger an event. You can select two sets, and if these sets collide, then based on the condition you have here, it's going to trigger an event. And all these events are going to be shown under animation player. You can also select if you want to create a solid right on the time that they interact. You want to see intersection curve, or you want to just highlight the bodies that are colliding. Very similar to interference, you have animation measure that can trigger an event based on some measurement. For example, here, let's say I want to measure the angle between this face and this face, and make sure that the vectors are directed the way that you want, and then you can set a condition. Here, for example, I want it to be greater than 90 with a tolerance of hundredths of a degree. So if the angle is greater than 90, it will trigger an event that you can select here if you wanted to stop an event or not. Make active makes the measurement active in the motion navigation. Now what happens here, now I get an option under motion animation that here now I have this measure turned on. And if I turn it on, I get the measurement on the screen, and I can actually read the measurement, which is the angle between these two links. Now, as you can see, a stop on event is not checked, but if I go back and stop on event, here you see that it stops on the trigger. Now you see that it's not actually on 90 degrees because I don't have enough steps to stop it on 90 degrees. Let me play here and go a step back. Here you see that between the 90 degrees is between these two steps, and since there is not enough steps to stop exactly on 90, software is going to stop this step. So make sure the resolution of your simulation is good enough for this. And this is helpful if you want to stop the simulation here at some point and then go back to the assembly or modeling app. Now, how can you connect these two apps? Here you have this option of creating sequences or capture the arrangement. Sequence is just creating a couple of images from each frame of the simulation. So let's try that first. Now I have this sequence made and I can access it from the modeling app, but the more important one is this capture arrangement. Let's say I want to capture this arrangement. It will show me the time, and you can choose if you want to capture only this arrangement for this simulation, or you want to have it as a standard. The difference is that if you select isolated, and if you have a big assembly that only has one moving part, only that moving part will be on the arrangement. The rest of this stuff will follow the arrangement that they already had. So I go with the standard, and now I have the arrangement saved and I can use it in the assembly. So let's go back to the master part that I have here and take a look at the arrangement that we made. Now here, if you move to the assembly, you can select the arrangement. You can see I have a default arrangement which I was working on when I made this assembly, and now I have another one. And if I double click on it, you see that the assembly moves to the arrangement that we saved on the motion app. I can close here and start doing the rest of the design or modeling that I wanted to do. Similarly, you have the sequence here, and you can basically play the animation. Here I need to first select the sequence that we saved like this, and now if I play it, I'm gonna see the same exact same animation that I had in the motion. And also it saves the sequences here as frames, as you can see, under the sequence navigator. The only advantage of the sequence is that when you don't have access to the motion application, or someone is just doing the design on the modeling app and you are doing the motion simulation and you just want to share some animations of the assembly moving around. So let's go back again to the simulation app and continue on the analysis. Trace also makes a trace possible on the animation player. So I can select what object I want to trace, and this will create a sequence of solids now, not just images, but solids. So if I go to the animation player now I have trace available. And if I click on trace, this starts to trace the object that I selected based on the time step that I have. Now if I close, you see that these are actually bodies, so you can actually do some design on them. And here, if I go back to the assembly here, you see that under the part navigator, I have actual bodies that are made from tracing the object. And if I remove this, I can go back and also remove the feature group that contains all these traces. The animation camera will animate the camera for you, as the name implies, and then you have solved that you already have access on the home tab. And then under the animation player, you have XY results, which you can also access from here. You can populate the result into a spreadsheet. Unfortunately, right now my NX is not connected to Excel, but you can take all the results to Excel as well. Again, here you have create sequences. Then you have load transfer. This load transfer is also working with Excel. This is more useful to connect NX Motion to NX Prepost or Nastran, which is for simulating stress analysis and heat transfer and basically doing finite element. And to do that, you need to take the forces out of the motion simulation and apply it inside another application, which is a little bit advanced here and we don't need to use it. And then we have motion envelope. This is very similar to tracing, but instead of making multiple bodies, it will just create an envelope around that body. So if I click OK here, it runs the animation again, and you see if I play again here, you see this is the actual envelope that that object is moving inside. This is also appearing under the assembly. So if I go here to the part navigator, under the non-time step geometry, I now have this geometry that I can actually use it for design. So here I go to the modeling app, and then I can basically edit this. And this is very useful, for example, when you want to design a cover for this system or this mechanism here. Let's say you want to cover this part and you can easily see this envelope, and then use that as a background to make a cover. For example, like this, and I can extrude this and then make a cover based on the extrude. Like this. And then I can just go back and remove this, and the remaining is the cover for this pendulum. Let's go back to the motion application, and as you can see, now I have a cover that fits the movement of my machine or whatever you have in your setup. So basically this is what you have under analysis tab, and these are the stuff that you can use here. Next, let's take a quick look on the couplers. Couplers are basically connections between the joints. For example, a gear coupler can be used to connect two revolute joints. In Recordine, the only option is for a revolute joint, and the condition is that both joints should be on the same motion body. I don't have the same. I don't have two revolute joints that share a motion body as a base, so here I can't use it. But you can connect two rotational joints to each other, and it will automatically read the ratio based on the radius that you have selected while you were making the revolute. Next is the rack and pinion, and this could be used to connect a slider joint to a revolute joint. So the revolute acts as a pinion, and the rack is going to be your slider, and the ratio will be set by the length of the slider that you're selecting. But you can also customize the ratio as you wish. Then we have the cable. The cable is basically like a bicycle brake cable, and you can only use a slider. So the sliding of the first slider joint is going to follow the second one. So if you pull and push one of the joints, the other one is going to follow with the ratio that you provide. And last but not least is a more general function of 2 and 3 joint coupler, which you can connect joints with any kind of condition that you want to have. You can also make gears or cable connection with this type of connection because it gives you more general options. For example, let me here turn this fixed joint to a revolute joint first, and then I can use a 2-joint coupler to couple these joints with a scale of 1, for example, and you see a line that represents this type of connection. Now let's solve and see the result. Now as you can see, because these two joints are coupled to each other, it doesn't allow the second arm to move. And we can change the condition here under the couplers. I can change the scale to 5:1 by changing also the rotation direction. And let's solve it again and see the result. As you can see, because I changed the direction and there is a ratio, the second arm is actually forcing the first arm to move, and at the same time, the whole thing is acting as a pendulum.